Hello there and welcome to A-Level Further Maths. Here we're going to do the first video they've ever done that's just a bit of fun. It's hyperbolics just for fun. We're going to see the link between hyperbolic functions and normal trigonometry. And in that we're going to see how it links in with complex numbers as well. So the first thing I'm going to show you is that cos of ix is equal to cos of x. So how are these two equivalents? Well, let's get started with the left-hand side. And we recall the definition of cos, which is e to the x plus e to the minus x all over 2. The next thing we're going to do is we're going to substitute in x for ix. So in this formula here, we're going to replace x with ix, which is exactly what we've got on the left-hand side there. So now it's perfectly equal to the left-hand side. Okay, let's start rearranging this now. What could we do with this? Well, these things here look to me like complex numbers, where the modulus of the complex number is 1 and the argument is this value x. So what we're going to do now is we're going to convert this exponential form of a complex number into modulus argument form. So that's going to be cos x plus I sine x plus cos minus x plus I sine minus x. With these negative angles, we're now going to apply some rules of trigonometry, whereby cos of a negative angle is equal to the cos of that positive angle, and sine of the negative angle is minus sine of that angle. So we're going to apply those rules. Basically, the negative disappears from the cos, and the negative moves to the front of the sine. We can now simplify what we've got here, and you can see we have a positive I sine and a negative I sine which cancel each other out. So we're left with 2 cos x on the top and divide by 2 on the bottom from the definition originally and cancel those 2's out, and we've got cos. So there we are, we have just proved that cos ix is equal to cos. This is going to be the first of 4 identities that I'm going to prove, and then we'll have a little bit of fun with them afterwards. So cos ix equals cos x. What about sine then? Is there a similar rule for sine? Well, nearly. It's slightly different though. It's sine ix equals I sine x. So there wasn't an I in front of this cos one, but there is an I in front of this sine one. And it's done in a very similar way. Starts with the definition of sine, which is e to the x minus e to the minus x over 2. And then replace x with ix, so that you've got exactly what you want on the left-hand side. Again, these look like complex numbers, so we'll write them out in modulus argument form, and then simplify the trigonometry with the right-hand one. And then what do we have that can simplify? Well, we've got the cos x that is a positive and a negative. When you expand these double brackets, the I sine x will become positive, so it'd be 2I sine x. Divide the 2's on both sides, and you've got exactly what you want on the right-hand side. So that's why there's an I at the front of sine x. It's because it refers to I sine x in the modulus argument form of a complex number. So that's identity 2 of 4. Let's move on to the third one. And the fourth one, so the third one, is cos ix equals cos x. So actually you can move the I in the cos one to wherever you wish it to be. So let's start with that rule that we started with from above, that cos x is equal to cos ix. And what we'll do first is we'll replace x with ix, so that the I is now in the cos. But then we'll have 2 i's multiplying together inside the cos function. And what do you get when you multiply 2 i's with each other? You'll get a minus 1. So it's minus x inside the cos. Now, how can we prove this back round to cos x? Well, if we think about the definition, it's going to be cos of minus x. So it's going to be minus x here plus minus minus x. Cancel out those 2 minuses to make it positive, and you're back to the definition of bog standard cos again. So cos of minus x is equal to cos of x. You can also see that in the graph that it's symmetric over the y-axis. So there we are, lovely. We've proven that left-hand side equals right-hand side, and that cos ix equals cos x. And moving on to the final one, again it's basically moving the i's around in the sine one. So we'll take that identity from above and again replace x with ix. So we've now got the I inside the sine function. But here we're going to have two i's multiplying together, so it's going to be sine minus x equals I sine x. Now what we've got here, use the definition for sine x. And when we simplify this, what we'll see is that we'll actually get the negative version of sine x. So it's going to be minus sine x. Now what we have here is not quite the identity that we were looking to prove, because it's I sine ix equals minus sine x. So it's not quite what we want. So let's restart with those two equivalencies and divide by I on both sides. So divide by I and you get what you want on the left hand side, but now it's minus 1 over I. Now what is minus 1 over I? Well, minus 1 over I, how would you work it out? Well, if you take minus 1 over I and times top and bottom by I, then you're going to get minus I on the top and minus 1 on the bottom, so that is just equal to I. So do some simplifying and you'll get I sine x on the right hand side. And there we are, we've proven that the left hand side is equal to the right hand side, and voila. So we have our four identities. So it's a way of linking normal trigonometry, hyperbolic trigonometry, and complex numbers all in four nice convertible formulas. Now what can we do with this? Well, we can solve interesting equations like sine x equals 2. And how would we solve sine x equals 2? Well, we know that it's going to be a pretty difficult question to answer because sine has a maximum of 1 and a minimum of minus 1. So it can only be in between those two numbers when the answers are real. But we're going to work out what the solution is in complex numbers. So we'll start with sine x equals 2 and we'll use one of the identities from above. So what we'll do first is multiply both sides by I. And then what we've got is I sine x equals 2i, and that's exactly what the second identity is. Recall the definition from above, that's the second one up here. So I sine x is equal to sine ix. So now we've got a formula, now we've got an equation that needs solving in hyperbolics. Let's recall the definition of r sine from the definition. So it was ln x plus root x squared plus 1, but it's plus minus. In fact, there is a plus minus in this one here because A-level definition of r sine doesn't work for negatives because you can't learn a negative, but you can in complex numbers. So we are going to carry on with the plus minus here, but in the actual A-level further maths, you're not going to see a plus minus here because you can't learn a negative number unless you're in complex numbers anyway. So let's carry on with this as the definition of r sine. Effectively what we've done from this side to this side is r shined both sides. That will get rid of the sine on the left hand side, so it's now just ix, and we've applied the definition of r sine on the right hand side as this expression here. Simplify what you get and you get 2i plus or minus the square root of minus 3. And we can split up the square root of minus 3 into square root of 3 times I, so we can effectively factorize out the i's from both of these two components inside the ln there. The next thing we'll do is we'll use the law of logs to split up this multiply, so it's now just ln 2 plus or minus root 3, add ln I. And then once you've done that, rewrite the complex number I in exponential form on the right hand side, and you'll get e pi by 2 I. Remember, I is a complex number itself with modulus 1 argument of pi by 2. So eventually, once you've simplified this, you're going to get pi by 2i and cancel out the ln and the exponential there. The last thing for us to do is to now get rid of this I on the left hand side. So we'll divide through by I, and when you divide through by I, it's the same as actually multiplying by minus I. So you'll get rid of you'll put a minus I in front of the ln, and then you divide by the I on the back here, so it's now pi by 2. So there we are, that's the answer, well that's one of the answers anyway, but remember that with the sine curve it repeats itself every 360 degrees or every 2 pi radians, so actually the full answer for this is this expression here. X equals I minus I ln brackets 2 plus root 3 and then plus 2 pi by 2 and then repeat itself every 2 pi radians from there. So there we are. You can solve sine of x equals 2 or sine of x equals 3. All of those numbers still work. So yeah, that's pretty interesting. I thought that was quite fun, really. Also, something just to finish up on is solving an equation like this. E to the x equals minus 5. It's got nothing to do with hyperbolics. I just thought it'd be fun and interesting to look and solve it. So we know that e to the x is only positive. The graph of e to the x for real numbers is only positive, but this question can be solved in complex numbers. What we'll do first is we'll treat minus 5 as if it were a complex number. So if it's on the Argand diagram, it's over here, where its modulus is 5 and its argument is pi, an angle of pi rotation around from the real positive axis. So minus 5 can be thought of as the complex number 5e to the pi I. Now to work out x, we'll have to ln both sides, so we'll apply ln to both sides. On the left-hand side, the ln and the e will just cancel each other out, so it's just x. And then what I'll do is I'll split up the 5 and the e using the law of logs, where you will split up a multiplication with an addition of logs. So it would be ln 5 plus ln e to the pi I. Then we can cancel out this ln and e there, and that will end up with our answer, which is x equals ln 5 plus pi I. And there we are, that's the answer to that equation. So it's not solvable in real numbers, this little equation, but it is solvable in imaginary numbers. Okay, a little cheeky question for you to have a go at your own there. It's not related to any exercise or any page reference number. It's just a question I thought you might be interested in solving. So pause the video, give this question a go. Okay then, let's start going through the answer then. So what identity could cos turn into so that it will help us solve this equation? Because we're going to want to turn it into hyperbolics, really. And I think it's this first identity that we have up here, that cos of x is equal to cos ix. So I'm going to turn this equation into a cos ix equals 2 equation. Okay, the next thing I need to do is get rid of the cos from both sides then. So it's ix equals cos inverse, or r cos of 2. Now the definition of r cos, I've just got the formula booklet up here. R cos of x is equal to ln, and it's probably going to be x plus or minus in complex numbers, the square root of x squared minus 1. Alright then, so that's the definition. So let's now apply it to what we've got here. It's going to be ln brackets 2 plus or minus the square root of be 4 minus 1, that's 3. And then we'll divide through by I, so it's going to be x equals minus I ln 2 plus or minus root 3. And there we are. So we'll probably then have to do a plus 2 pi n, because we know that the cos graph repeats itself every 360 degrees. So there we are. That's the answer to this question. So so there we are. Hopefully you found that little bit of hyperbolics there potentially interesting. And actually the formulas that we're going to use, I'm going to actually use them in the next hyperbolics lesson. So it's not wasted your time at all. So thanks very much for watching. Hopefully you found that useful, and see you in the next video.